man. They're all crazy. I'm sure y'all got a story to tell.
Good afternoon, ladies and gentlemen. My name's Joe Exotic, and this is Sarge.
Oh, hi there. Sorry, you just caught me doing some Netflix and relaxing. I hope you've been well this week, and hope you're looking forward to learning some new math. We're all done talking about graphs of sine and cosine, and we finished that unit. So now it's actually time to start our exponential functions unit. So we're going to learn about exponent laws, which are something that you might have seen in grade 9. After we do a few lessons on exponent laws, we're going to move into exponential functions, modeling with exponential functions, and that kind of stuff. So I hope you enjoy this new unit, and let's check out our next lesson together.
She's a plain out hypocrite. She literally does everything that I do.
So like I said, we'll start by looking at some of the basic exponent laws. And before we do that, let's make sure that we're okay with some terms. The term power. The term power refers to this entire expression, 3 to the power of 4, which of course is a shortcut for 3 times 3 times 3 times 3, which is also 81. So 3 to the power of 4, a power has a base, in this case, the base is 3, and it also has an exponent. In this case, the exponent is 4. And you can think of powers as basically being shortcuts. Ancient Greek mathematicians started taking expressions like 3 times 3 times 3 and simplifying that by writing that as 3 to the power of 4. Now, even though exponents are shortcuts, based on the definition of exponents, there has to be certain things that are true, certain rules, and those are exponent laws. And we're going to start looking at those laws right now. The first one involves multiplying powers of the same base. For example, 5 to the power of 4 times 5 to the power of 2. Now, 5 to the power of 4 can be written as 5 times 5 times 5 times 5. And 5 to the power of 2 can be written as 5 times 5. Now, notice I'm multiplying a bunch of 5s here. 4 of them and 2 more. This can also be written as 5 to the power of 6, since there are 6 5s. Let's look at 2 to the power of 5 times 2. 2 to the power of 5 is 2 times 2 times 2 times 2 times 2. And then multiply that by one more 2. And sure enough, we get 2 to the power of 6. 1, 2, 3, 4, 5, 6 2's there. Finally, with our x's, x squared is x times x. Times that by x cubed, which is x times x times x. And if I take a look at this one, those dots mean multiplication, by the way. I'm multiplying 5 x's together, which can also be written as x to the power of 5. Now, I think the pattern is probably pretty easy to see here, and many of you probably already know this. Take a look at the first one, 5 to the power of 4 times 5 to the power of 2. Sure enough, I get 5 to the power of 6. 4 plus 2 is 6. If I look at the last one, I've got x squared times x to the power of 3. 2 plus 3 is 5, x to the power of 5. And in the middle one, as long as I realize that that is the same as 2 to the power of 1, then I can say that 5 plus 1 is 6, and sure enough, I have 2 to the power of 6. There's your first exponent law, the multiplication law. When you're multiplying powers where the base is the same, you can add the exponents. Algebraically, that rule is a to the power of m times a to the power of n equals a to the power of m plus n. So let's do a couple examples. 2 to the power of 8 times 2 to the power of 3 is 2 to the power of 11, 8 plus 3. Now you might be saying, why do I need to do this? Well, you don't necessarily. You could say, for example, 2 to the power of 8 is 256. And 2 to the power of 3 is 8. So you could say, why can't I do 256 times 8? I'll get the same thing. And the answer is, yes, you will get the same thing. It's the same as 2 to the power of 11, which I believe is 2048. But that doesn't work when you're dealing with algebraic statements. So y to the power of 4 times y to the power of 10 is y to the power of 14. There's no way to figure that out kind of using your calculator. Okay, let's move on to the next rule, which will involve division of powers. So in the first example, I'm dividing powers of 5. Now we're actually going to change that division symbol into a fraction symbol. It's going to make things a little bit easier. Now on the top of the fraction, I have 5 to the power of 4, which is 5 times 5 times 5 times 5. And on the bottom, I just have 5 times 5. Now with fractions, we can divide the numerator and the denominator, the top and the bottom of the fraction, by the same amount. So let's first divide the top and bottom by 5. Let's divide by 5 again. Now basically I have made the denominator into 1 because I've divided both the 5's out. And in the numerator I have 2 5's, or 5 times 5, which is the same as 5 squared. Let's do the same thing again with the x's here. In the numerator I have 5 x's. 2, 3, 4, 5. And in the denominator I have 4 of them. If I divide x's the same way I did in the other example, I'll divide an x here and an x here, an x here and an x here. You can see they're dividing out. Until finally, I've divided by x 4 times. There's a 1 or nothing left in the denominator and just an x left in the numerator. You could also think of that as being x to the power of 1. So you can see that the exponent in the denominator tells you how many times you can divide out whatever number it is you're working with, whether that's 5 or x or whatever else. And the final exponent we get is from subtracting. 5 minus 4 is 1, 4 minus 2 is 2. So there's our division law for powers of the same base. We subtract the exponents. So to divide powers of like bases, we subtract the exponents. Now notice this like bases is very important. The bases must be the same. Otherwise, you can't do that. Okay, if I was talking about, for example, dividing 5 to the power of 4 divided by 3 squared, well, now the 5's and the 3's don't divide out, so it doesn't work. So it's only for powers of the same base. For example, 5 to the power of 11 divided by 5 to the power of 8 is 5 to the power of 3. Slightly more difficult example. First, let's use our rule for multiplication. This is y to the power of 8 divided by y to the power of 4, and then we subtract to get y to the power of 4. The next rule for dealing with powers we're going to talk about is called power of a power or power on a power. For example, look at the first one here, 10 to the power of 4, and then take that value and square it. So we could look at it like this. Let's look at the squared first. When you square something, it means you multiply it by itself. So we're really doing 10 to the power of 4 times 10 to the power of 4. Well, our rule for multiplying powers says you can add the exponents, and that's 10 to the power of 8. By the way, powers of 10 are very easy. Start with a 1, and then the exponent tells you how many zeros. So in this case, there'll be 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, or 100 million. 5 squared to the power of 3. Okay, let's start with the power of 3. The exponent 3 says multiply this by itself 3 times. 5 squared times 5 squared times 5 squared. And again, our rule for multiplying powers says you can add those exponents. 2 plus 2 plus 2 is 6. You get 5 to the power of 6. If it helps, you could imagine, 5 squared, 5 times 5, times 5 times 5, times 5 times 5, and sure enough, you'd have 5 to the power of 6, 6 5's there. Well, this pattern isn't too hard to see either. Notice 4 times 2 is 8, 2 times 3 is 6, and that kind of makes sense. Here you're making 2 groups of 4, and here you're making 3 groups of 2. So a to the power of m to the power of n is a to the power of m times n, or just write that as mn. So to simplify power on a power or power of a power, we multiply the exponents. For example, 2 squared to the power of 5 is 2 to the power of 10. 2 times 5 is 10. Now you might be saying, well, isn't 2 squared to the power of 5 just 4 to the power of 5? Absolutely. 4 to the power of 5 and 2 to the power of 10 are both the same number. I believe it's 1024. However, when you move to the next example, as soon as you're dealing with algebra, okay, you can't take that approach. X squared to the power of 9, 2 times 9 is 18. That's x to the power of 18. For our next exponent law, we're going to look at what's called power of a product. Now keep in mind, product means multiplication. Now this is different than multiplying powers. This is a power where your multiplication is the base. So for one example, we could look at 2 times 3 cubed. Now 2 times, when you cube something, that means you multiply by itself 3 times. So we could write this as 2 times 3 times 2 times 3 times 2 times 3. Now, the nice thing about multiplication is order of multiplication doesn't matter. When you're multiplying a whole bunch of things together, you can scramble up the order however you want. It won't make a difference. So in this case, I could imagine all the 2's beside each other and all the 3's beside each other. Notice there are 3 2's, so I have 2 to the power of 3, and there are 3 3's, 3 to the power of 3. So 2 times 3 to the power of 3 could just be written as, sorry about that, as 2 cubed times 3 cubed. Now you might be asking, well, that's kind of silly. I mean, 2 times 3 to the power of 3, order of operations just says that's 6 to the power of 3. Absolutely, that is correct. You would never use the rule we're talking about right now for an example like this. It just wouldn't make any sense. 6 to the power of 3 is a fine answer there. But when you have a power of a product, it generally looks like the second example here, where one of your terms is a variable. I don't know what 2 times x is, but I can still do 2 times x to the power of 4. It's 2x times 2x times 2x times 2x. Now, just like in this last example, I can think of all the 2's being together. 2 times 2 times 2 times 2, which is 2 to the power of 4, and x times x times x, which is x to the power of 4. That actually simplifies to 16x to the power of 4. So you can see what happens with the power of a product. Notice 2 times 3 cubed was 2 cubed times 3 cubed. And 2x to the power of 4 ended up being 2 to the power of 4 times x to the power of 4. Now in general, ab to the power of n can be written as a to the power of n, b to the power of n. Let's look at a few cases where we might use this. 2x to the power of 7 is 2 to the power of 7, x to the power of 7. Or if you use your calculator, 2 to the power of 7 is 128. For the next one, a little bit more difficult. Here I can think of my product as being negative 3 times x squared, where a is negative 3 and b is x squared. Okay, so the first thing I do is negative 3 to the power of 4. I do technically need those brackets there. And then x squared to the power of 4. Negative 3 to the power of 4 is positive 81, so there's an even number of negative 3s, so negative times a negative gives you a positive. And then x squared to the power of 4, we can use our power of a power rule, that's x to the power of 8. Okay. Now by all means, as you get good at something like this, you could simply skip to that last step right there. Now as much as this is a rule, ab to the power of n is equal to a to the n, b to the n. Sorry about that. Sorry, no, I'm having some trouble there. This is not a rule. A plus b to the power of n is not equal to a to the n plus b to the n. So just be careful with that. Don't go making up exponent rules. For example, 2 plus x squared is not equal to 2 squared plus x squared. That is not a rule. In fact, from what we learned earlier in the course, that's 2 plus x times 2 plus x, and you got to use FOIL to expand that. You'll get 4 plus 4x plus x squared. So just be careful you don't go inventing exponent laws. So yes, over multiplication, it's kind of like, the exponent is raised to the power of both things in the brackets, but that is not true when you do addition, so just be careful with that. In our last example, we look at powers with rational bases. So a rational base means a fraction base. Now the previous example was products. The opposite of a product is a quotient, a division statement. So you could also say that this is a power rule for dealing with bases that are quotients, but I think it's easier to think of them as being just fraction bases. Let's look at 3/4 cubed. 3/4 cubed is 3/4 times 3/4 times 3/4 times 3/4. To multiply fractions, we multiply numerators together and denominators together, or tops together and bottoms together. Well, 3 times 3 times 3 is 3 to the power of 4, and 4 times 4 times 4 is 4 to the power of 4. Now that happens to be 81 over, I believe, 256. Let's look at 1/5 to the power of 4. That would be a fifth times itself 4 times. Now 1 times 1 times 1 4 times would be 1 to the power of 4, and this is 5 to the power of 4. So we have 1 to the power of 4 divided by 5 to the power of 4. Now we never need to write 1 to the power of 4. 1 times itself 4 times is still 1. So we go 1 over 5 to the power of 4. Okay, I don't really care in this case what 5 to the power of 4 is. What I do care about is you noticing this little pattern, that 1 over 5 to the power of 4 ended up being 1 over 4 divided by 5 over 4, and 3/4 to the power of 3 ended up being 3 to the power of 4 over 4 to the power of 4. And so you can see for the rule here, in general, a over b to the power of n is equal to a to the power of n divided by b to the power of n. And let's try the examples below. So the first one, 2/9 squared is 2 squared divided by 9 squared, or 4 over 81. The next example, we have -1 cubed divided by 4 cubed, which is -1 over 64. And for the last one, -1/2 to the power of 4 is -1 to the power of 4 divided by 2 to the power of 4, which is positive 1/16. As a review, here are all of the exponent laws we talked about in this video. Okay? Multiplying powers, dividing powers, power of a power, power of a product, and power of a quotient, or powers with rational bases. Often we use more than one of these rules when we're evaluating expressions with exponents. Okay, so let's simplify the following. All powers of x. As soon as I have an expression that is all powers of x, I know that I should be able to write this as one single power with a base of x. Now to start with, we need to take a look at what's in the middle here, the power of a power. We multiply exponents. We change that to an x to the power of 15. Looking at the numerator of that fraction, I can add the exponents, keeping in mind that's a 1, because I'm multiplying. So 2 plus 15 plus 1 would be 18. Last step, dividing powers, we subtract the exponents, and we get x to the power of 8. So this big ugly expression here is just the same as x to the power of 8. Keep in mind that means whatever number you sub in for x, you will get the same thing if you subbed in here as if you just were to sub in here and raise it to the power of x. Next example. Okay, if I look at this first one here, I might be tempted to say square 2 and square 3, square 2 and square 3. However, it makes a lot more sense to treat these all as if they're powers with the same base, and that base being 2/3. So what we can do in that case is we can just add the exponents together, and we get a power with a base of 2/3. 2 plus 2 is 4, plus 1 more is 5. That's 2/3 to the power of 5. Okay, that is the same as 2 to the power of 5 divided by 3 to the power of 5. Now 2 to the power of 5 is 32, and I believe 3 to the power of 5 is 243. Okay, this really is the line I'm more concerned with, though. Okay, for the last example in today's lesson, let's look at the numerator there. 2x squared to the power of 3 is 2 to the power of 3, and then x squared to the power of 3 is x to the power of 6, power of power, multiplying the exponents there. How do I go from here? Well, I would just evaluate 2 to the power of 3. It's 8. And I get that right there. And 8 divided by 4 is 2, and x to the power of 6 divided by x to the power of 3 is x to the power of 3. There we go. Okay, good luck with the sign questions that go along with this, and I'll talk to you soon. Bye for now.